negative b plus or minus square root b squared minus 4ac divided by 2a.
Alright, welcome back. This is lesson number 36, and this is going to be a quick video. You're hopefully working on this after you have recently finished your Unit 6 test. So in this video, we're going to be focused on a concept called base matching. Alright, and what base matching does is it helps us solve some exponential equations. So before we go too far, you don't have to write this down, but just check this out, right? You know how to solve this, you know how to solve this, you know how to solve this, you know how to solve this. But this equation right here, now you all, if you had a little time to think about it, could eventually get that in your head and tell me that the answer is x equals 3. But you know how when we do this, we use inverse operations and we like do something to both sides to get the answer? You guys do not know at this point in math how to do something to both sides here. And we're not even going to learn that today necessarily, but we are going to come up with a way that we can algebraically show our answer to something like this rather than just doing it in our head. So if I go back to the front here, I'm quickly explaining that an exponential equation is an equation where the variable is located in the exponent. So see how all these problems I've got on the page here, they all have x in them, but x is always upstairs in that exponent. So it's a little bit different than, like, you know, this 3 to the x plus 5 is much different than if I just wrote 3x plus 5. And I'm saying a strategy we can use is called base matching. We're going to learn a different strategy down the road, like in a, I don't know, next week or something like that. But for now, just base matching. So let's look at the first one, and then we'll have to stop it and talk about a few things. But in this first one, the base is always like the big number that is being raised to something. So let's notice here, I'm going to break out a different color. Let's notice that the bases match, right? Those are both 3. So if these things are the same and this is an equation where both sides are supposed to be equal, it follows that x plus 5 must be the same as 2x minus 7, right? If they're both 3 to the something and they're supposed to be equals, then whatever they're being raised to has to be the same. So then we would just solve this, right? Move the 7 over, that'd get you 12. Subtract this x over, that'd get you x. And wow, that was very, very easy. But we run into issues in problem 2, right? Because this time, like the first problem was really easy because these matched, hence the name base matching. But here we have an 8 and a 64, so they do not match. So we're going to have to, you know, this is what we're learning, coming up with a new strategy for dealing with a problem like this. First, I want to start with a little bit of exponent review. So let's just choose the base 2, for example. And I'll start with, what if I gave you the problem 2 to the 0 and asked you to evaluate that? Well, anything to the 0 power is 1. How about 2 to the first power? That'd be 2. 2 to the second power is 4. 2 to the third power is 8, right? That should all be easy stuff. But how about when we go the other way? Remember us learning that negative exponents always make fractions? Like exponents mean to multiply over and over. So negative exponents mean to divide. So 2 to the negative 1 is really 1/2. 2 to the negative 2 is 1/4. 2 to the negative 3 is 1/8, and so on. So we've got this big idea that we're going to need to be using once we start working through that. One other thing I want to review. If I were to put this on your paper, remember that at some point in the year way back we learned that radicals and fractional exponents are kind of interchangeable. So this is really, we assume the exponent's 1, we assume the index is 2. So that's actually the same thing as 2 to the 1/2 power. So now that we've got kind of this idea of how exponents work, let's see how we're going to use this. 8 and 64 do not match. But what I want to think about is there a way that I could express these things to get them to match? So watch what I mean. I'm going to keep that as 8 to the 4x. But couldn't I rewrite that as 8 to the second power? Because 8 to the second power is equal to 64. So I haven't done anything mathematically incorrect there. All I did is rewrite it. But now look, see how the bases match now? So now I can use the same strategy I did over here. I can drop the exponents down. However, how do I deal with this? This is a power raised to a power. And our rule for that is to multiply the exponents. So 2 times 3x is 6x. 2 times 2 is 4. And now I can just solve that to get x equals -2. Okay, so I'm rewriting one or both of the bases to get them to match and then going from there. So like this one looks almost the same, but like your first instinct might be to rewrite that as 8 to the second power, but that's really 8 times 2. So I cannot use 8 as my matching base here. So I need to think about what's a number that when we multiply it exponentially goes into both of this. Well, couldn't I rewrite 8 as 2 to the third power? And rewrite 16 as 2 to the fourth power? That would work, right? Because 2 to the third is 8 and 2 to the fourth is 16. So that gives me the matching base that I'm looking for. So I can forget about the bases and use power to a power. So I'm doing some multiplying there to get to here. Be -20, x equals -20, so x must equal 1. So the solving part is easy. The getting there, that's what we're really working on. All right, next one, we're looking at these two bases. We have 27 and we have 1/9. So what is a common number that could exponentially go into both of those? Well, 3 would work. So if I rewrite this as 3 to the third, how do I express this with a 3? Well, it's a fraction, so it must be a negative exponent, and 3 to the second is 9, so that's just got to be 3 to the -2. Now I've got matching bases, so I can forget about them. Power to a power, we multiply. And 3x equals 10, x equals 10/3, right? You're not always going to get perfectly clean answers, so this one didn't work out as nicely as the other ones. However, it is still correct. Alright, in this problem we have two fractions, so we're going to be working with some negative exponents. This one could be 4 to the -1. And this, remember, we're trying to match the base. So saying like 8 to the -2 here would not be worthwhile, because then 4 still wouldn't match 8. So how many times does 4 multiply into 64? We could do 4 to the -3 and have that set up. Now that our bases match, we're good to go. So multiply that in, you get -3x minus 3 equals -6x plus 21. 3x equals 24, x equals 8 when we work our way through that. So I'm not spending, I'm motoring through the solving because that should be the easy part. The base matching is really what we're working on. How do we get there? 3 more in this bottom row. I was trying to keep it under 10 minutes. I don't think I'm going to make it. So this, we have 7 and 7, so that's fine. We need to know that the radical can be rewritten with a fractional exponent. We assume the exponent's 1, we assume the index is 2. So that's really the same thing as 7 to the 1/2 power. And this one didn't need to change at all, because now that we've done that, these match. So I can say that 9x minus 13 equals power to a power we multiply, so that's going to become x plus 3. We got 8x equals 16, x equals 2. So if you see radicals and you're trying to base match, convert them into exponential form with a fractional exponent and then go from there. Now the last two, unlike the other problems, now there are 3 things involved and there is a multiplication symbol. So let's walk through this. What base will work for all 3 of these? Well, 5 will work. So I could do 5 to the x times. I'm going to rewrite that as 5 squared to the x plus 2. And I'm going to rewrite the third one as 5 to the third to the 5x minus 1. So now that all the bases match, I can forget about them and drop the exponents down. So that's just x. However, when you multiply things with the same base, what do you do with the exponents? When we multiply, we add exponents. So that really turns into a plus sign. and I distribute there, 2x plus 4 equals, distribute here, 15x minus 3. So this is 3x plus 4 equals 15x minus 3, so 7 equals 12x. X must equal 7/12. So pick a base that works for all of them. When you're multiplying, you add exponents. So when we drop things down, I turn that into a plus sign. Then I just solve from there. So the last one is very similar to what we just did, except for now there's going to be a quadratic involved. So what base will work for all these? Well, 2 will work for everything, because that could be 2 to the 5th to the x. Since that's multiplication, actually I'm not going to do that yet. I shouldn't do that until I'm done base matching. That one does not need to change because it was already 2. And 8 could be written as 2 to the 3rd. Now that we have matching bases, I can get rid of them. This is 5x. Since it's multiplication, when we multiply, we add exponents. This is already 2, so I can just drop that down and drop this down. So we get to there. Let's get everything on one side by subtracting 3 and reorder it so it looks nice. Then this is a really easy one to solve by factoring. It is possible you'd have to use quadratic formula. Like there's one on your homework where you're going to have to use quadratic formula, but most of the time, like most quadratics we do in this class, you'll be able to factor them and solve them. So a little longer than the 10 minutes I promised, but not too bad. Hopefully this felt like an easy lesson and you can go knock out homework 36, which for some of you will probably be like a 10-minute endeavor. Some of you it might be closer to 20, but it should not take you very long. All right, have a good day.